Let's start with a filter that is just a rectangle impulse response. So that's our running sum. If you don't normalize it, this is something we analyzed in 320. It's a running sum filter. It's also analyzed quite a bit in DSP First, the Georgia Tech textbook for signal processing at the undergraduate level. And so its impulse response is just a rectangular window. And let's use it as a filter, and we'll see that the output Y is a convolution of this impulse response with X. And so here's the general equation for convolution. And because the impulse response is just a finite rectangle, it truncates this infinite sum to lie between 0 and capital N minus 1. So the length of the impulse response is capital N minus 1. That's going to be the length of our DFT, just as a preview. And so this running sum is then our filter output. So Y of n is just X of n plus the previous input sample plus the last n sample. So it's the current and previous n minus 1 samples. So you could also think of it as an unnormalized moving average filter. It's just a running sum. And then the transfer function is easy to write down. You just replace delays by powers of z inverse and use the closed form for the closed form expression for a sum of a geometric series, and you get 1 minus z to the minus n over 1 minus z inverse. So that's our closed form transfer function. And now we can specialize that to the unit circle and get the frequency response.